Hey Royals, this is a summary of lesson 5.9, and I just want to show you a couple of other examples of using log properties before differentiating. First thing I want to do is just summarize all of our new exponential derivatives. Let's go through this in the order that we discovered them. We discovered a special base exponential function whose derivative was coincident with the original curve. Then we looked at the derivative of the inverse of this relationship, the derivative of the natural logarithm. Its derivative was the reciprocal of x. Both of these you can probably use a sketch as a bit of a memory aid. Draw yourself exponential curve. Think about the rates of change. Hey, look, they're exponential too. And then recall there's some special base out there whose function's derivative looks exactly the same as the original. Draw an inverse of that relationship. There's my sketch of y equals the natural logarithm of x. And think about what this derivative would look like. Rates of change diverge. They increase without bound as x approaches 0 from the right, and rates of change approach 0 from above as x grows without bound. And that looks like my parent reciprocal curve, except it has that restriction that we haven't been too worried about, that it's only the right-hand side of that rectangular hyperbola. For the general functions, the general logarithm or the general base exponential function, we just have a conversion to do. If we have the derivative with respect to x of b to the exponent x, it too will be an exponential function, but it's going to be a vertical stretch of that exponential function by the natural logarithm of your base. This rule actually works above. This is a more flexible rule, I suppose, but I don't feel the need to write e to the exponent x times the natural logarithm of e, because the natural logarithm of e is 1. That same conversion by a natural logarithm occurs over here if I take the derivative with respect to x of a general logarithm, log base b of x. It will be a factor of the reciprocal of x. That factor is going to be the reciprocal of the natural logarithm of my base. So there's a lot of patterns in here that you can use to develop some memory aids. The nice thing about it as well is that in the lesson we did go over the development of these. So if you find yourself in an exam situation and you don't remember these derivatives, then just figure them out on your own by using our log properties. Speaking of log properties, let's take a look at 2 examples from the lesson. I think this one was example B, where the function was y equals 5 to the exponent 2x minus 3. And there's not a ton of properties that we can use here, but I'll just use this as an early introduction to the idea of logarithmic differentiation. I am allowed, if I want to take the natural logarithm of both sides. I can take any logarithm, but I'll choose the natural logarithm since its derivative is a little bit simpler. That'll give me the natural logarithm of y is going to be equal to the natural logarithm of 5 to the exponent 2x minus 3. And now I have a property that I can use, excuse me, while I shift this. I have the power of a power. So I'm going to keep my base and multiply these exponents together. Be careful here, your exponent is polynomial. It will need to be surrounded in parentheses. And now I can take the derivative with respect to x on both sides. And I will have a chain rule here. The derivative of the natural logarithm of a function is going to be the reciprocal of that function multiplied by the derivative of that function. And here, I think I just have a constant multiple rule. This is going to be the derivative of this function multiplied by that constant multiple. So let's try 2 times the natural logarithm of 5. I'll isolate dy by dx there. I multiply both sides by y, and I get 2 times the natural logarithm of 5 multiplied by y. But usually, we will be expected to come up with expressions for the derivative in terms of x. You've seen questions where you were implicit differentiation questions, where you were told to find an isolated expression for dy by dx in terms of x and y. Here you may be told, or you might be expected in your homework to understand that if reasonable, you should be able to find an expression in terms of x for the derivative. What's this y? This y right here is 5 to the exponent 2x minus 3. I don't think this is much faster than saying that the derivative of this base exponential function is going to be the base exponential function multiplied by the natural logarithm of its base multiplied by the derivative of its exponent. That seems like a one-step process there. But again, if I'm ever worried that I'm forgetting something, it's nice to know that I can figure it out more than one way. Let's take a look at another example where our property is maybe a little bit more useful. What letter was it? I think it was letter, I changed the letters, A, B, C, D, E, maybe F? No, F is a pain. E. You can find it on your lesson if this letter is wrong. It was y equals log base 5 of 3x plus 2 to the exponent 4. Which of course should be interpreted as log base 5 of the fourth power of 3x plus 2, not the fourth power of the logarithm. So property choices. I could choose to rewrite this using the power of a power rule. Notice it's a little bit more intuitive than the last case, I think, because I already have a logarithm, so I'm ready to use that property. So what I'm doing here is I am exchanging the chain rule, or the power of a function rule, for a constant multiple rule. And I'll let you decide which of those two rules is easier to use. If I differentiate from here, I think things will work out just fine. Let me swing around to this side. I'll say dy by dx then is going to be 4 times, let's see, the derivative of a logarithmic function is going to be the reciprocal of that power multiplied by the reciprocal of the natural logarithm of that base. And that felt pretty fast. It's probably about as fast as saying it's the reciprocal of this function, and then I have the derivative of the inside, which is 4 times 3x plus 2 cubed, except I don't have common factors to eliminate. Now, another option for dealing with general logarithms that some students like is always using a change of base formula to the natural logarithm. It might seem like a bad choice because you're introducing a quotient, and the quotient rule isn't anyone's favorite rule. It's not that difficult, but it does make things harder or longer. But the advantage here, and you could probably see this on your own without showing this step. I'm just going to try to make it explicitly clear, is that when I change this into a quotient, my denominator is constant. And someone once told me not to use the quotient rule when I have a constant denominator or a constant numerator, because it's kind of a waste of time. So it might take me a couple of steps to get here, but it might be worth it if it means that my derivative is going to be easier. From here, I'll say that my derivative is going to be a constant multiple of 4 divided by the natural logarithm of 5, multiplied by the derivative of the natural logarithm. Did I miss something from the last example? I think I did. I think I missed a chain. Let me catch it in a sec here. Multiplied by the reciprocal of my power. And here's what I missed. I didn't do the multiplied by the derivative of the inside, the derivative of my power, times 3. I should have done that back here as well, times 3. These two statements should look similar. They do now, but I did it correctly. And I could, whatever approach I choose to use, I could just squeeze those two together, or those expressions together into 12 divided by the natural logarithm of 5 multiplied by 3x plus 2, which should look like what we came up with on our lesson. Yeah, I think I might have just put the factor of the natural logarithm of 5 on the other side. As long as you're using brackets, it doesn't really matter on what side you place that. Okay. Keep your eyes out for opportunities to use log properties, and we'll have to use those in the future.